So continuing our discussion with the architecture of 8085, we last time discussed about the ALU components, the accumulator, the temporary register, the ALU itself, and the flag register. Uh, so this is what your flag register, what the 8 bits of flag register signify. There are 5 significant bits and 3 don't carry bits. So let's see how each bit functions and how each bit can be accessed of a carry of this flag register. So starting with the least significant bit, that is the carry flag. So carry bit will be set or reset depending upon the arithmetic or logical instructions, and it's one of the most frequently used uh, bit among this flag register. Fine. So it can be set or reset by any ALU operation. So both arithmetic as well as logical operations will affect the status of carry flag, and it's, as said, the most frequently used one. It's an accessible flag. That means we can actually set or reset. We can actually read or write both. We can read the status of this flag as well as modify the status of this flag from outside. Uh, Say, for example, we may have an instruction like this, JC2010. This actually means jump to memory location 2010 if carry is set. By set will mean that cy becomes equal to 1, and by reset will mean cy becomes equal to 0. Or we can also have an instruction like this, jnc 2050 jump to 2050 if carry flag is not set. Fine. So these are different types of instructions that will actually be used for. There will be other instructions also, we'll be studying them, that will be actually helping us to access the status of carry flag and accordingly make our program more intelligent and carry on various types of programming in 8085. So when is carry flag set? When any arithmetic or logical operation, basically, say for example, we are doing simple sum of two numbers, two binary numbers. This will result in 1 and 0. So this 1 will basically set the carry flag. That's like this carry actually that is generated here will actually cause the carry flag to set. It will become equal to 1, and if arithmetic operation will not result in the carry flag to set, it will become 0. So there will be various operations, arithmetic as well as logical operations, during which the carry flag may either be set or be reset. So this is flag number 1, the least significant. It is the least significant bit of the flag register. Uh, Along with the flag register, alongside the carry flag, we also have the fifth bit that I showed you last time is the auxiliary carry. Before we discuss parity, we'll discuss the auxiliary carry. AC. So when is this auxiliary carry used? It's again, it will be used for arithmetic operations, but it will be used in BCD type arithmetic operations. We have actually studied BCD numbers in your digital control systems, digital logic design. So when you carry out BCD arithmetic operations, BCD summations, at that time the auxiliary carry will actually be set or reset. The carry flag will not be affected by BCD operations. So in any operation, in any arithmetic or logical operation, so regarding with this BCD operation, if uh, a carry is generated from fourth to fifth position, AC is set or else reset. Fine. So we'll be actually dealing with uh, whenever any ALU operation will take place and of any 8-bit number, and if a carry is generated from the fourth to fifth position. Fine. So when we were actually discussing this, this was just an example. We'll be actually doing uh, arithmetic operation of 8-bit numbers. So if you are, say for example, you are doing summation of this number, and at the end you are actually getting a carry. This carry needs to be counted somewhere because the accumulator will actually only show this to us, this 8-bit number, but this carry will not be shown to us. So we can actually decide whether a carry was generated or not by actually accessing the carry flag. In a similar fashion, if say for example we are doing, we have a number like this, mm, we have two numbers, two 8-bit numbers, and on addition we actually will check whether the carry was generated when summation of when these two numbers were actually summed, whether the carry was generated from fourth to fifth position. In this case, in this particular case, there is no carry that's actually generated on addition from fourth to fifth place. So in this case, AC will be set reset. That means AC will be set to 0. If in case there was 1 here, fine, and this will become 0 and this will become 1. So in that case, AC would become equal to 1. Fine. So these two operations we need to identify when the auxiliary carry will be set and when the simple carry will be set. So carry flag will be set when any 8-bit numbers are summed up and you are getting a resultant. The resultant basically leads to a carry which will not be reflected in the accumulator. We in the last session I told you, whenever an arithmetic operation will take place, the result will actually be again stored in the accumulator only. Another operand will also be in the accumulator. Another operand can be accessed from the memory location that will be actually stored in the temporary register temporarily, and the resultant will be put in the accumulator. On accessing the accumulator, you will see only an 8-bit number. You will not know whether there was a carry or not that was generated. So for that, you like to access the carry flag. Similarly, if you are carrying out BCD arithmetic operation, you will be actually checking whether from fourth to fifth position a carry was generated, because when we talk about BCD numbers, actually 4 bits of data actually represent one number in a BCD. Whenever any ALU operation takes place and a carry is generated from 4th to 5th position, auxiliary carry will be set or else it will be reset. So we need to, this will be used for when we are actually carrying out summation of BCD numbers. Uh, Yet another significant flag register is a parity flag denoted by P. It's one of the most, it's again an important flag, but not used as much. So, uh, if we have an even parity, then the parity flag will be set. If we have an odd parity, then the parity flag will be reset. So, this is actually used in data transmission for error detection. Not use it quite often. Again, it's an accessible flag. So there will be instructions like JPE, JPO, JPE, JPO, jump if parity is even, jump if parity is odd. So parity basically means that how if you have an 8-bit number, if you have even numbers of ones, then it's known as even parity. If you have odd numbers of ones in that 8-bit number, then it's referred to as an odd parity. So if you, the resultant, so this will be used wherever we need to check whether we have even number of ones in the 8-bit number itself or odd number of ones in the 8-bit number. Fine. So for example, we have something like this 101101000. This is your 8-bit number, but there are 4 ones, so it refers to even parity. If you have a number like this where you have only odd number of ones, it refers to odd parity. So moving to next flag, we have the 0 flag. Uh, it is used frequently. It's also an accessible register, accessible flag, and you have uh, instructions like JZ, JNZ, jump if Z is set, 0 flag is set, jump if Z, 0 flag is not set. Fine. So whenever an arithmetic and logical operation will result in a number 0 in the accumulator, 0 flag will be set or else it will be reset. So after an ALU operation, following an ALU operation, if 0 is the result in the accumulator, then 0 flag is set or else 0 flag is reset. Fine. So you are actually adding up two numbers. You have two 8-bit numbers and you are adding them up. So this will definitely result in 0 0 0 0. You can also have a number like this 1 and 1 here. This will also result in a 0 zeros, while it will also produce a carry. So there can be two conditions. So in the earlier case, if you have a number like this will make 0 flag equal to 1. Carry flag will be reset. But if you have a number like this, The resultant is again zeros, but there is also carry generated. So this sets z equal to 1. This will also set carry flag equal to 1. So this is how you can actually distinguish between addition of two different types of numbers and the result itself. So for any non-zero result in the accumulator, the carry flag is reset. For a zero result in the accumulator, the carry flag is set. So we can differentiate now between different types of numbers being set by accessing various flags. Finally, we have the sign flag. So whenever an arithmetic and logical operation takes place uh, in a data byte and results in a data byte that whose MSB is actually 1, sign flag will be set, otherwise it will be reset. So following an ALU operation, result has MSB equal to 1, then sign flag is set, or else sign flag is reset. So this can actually be used for interpretation. You actually know that to show positive and negative binary numbers, how we basically place one at the as the most significant bit. So it will be actually up to the user to interpret whether this is a positive number or sign number, whether we are actually dealing with sign numbers or not. So you can have any type of arithmetic and logical operation, and that actually results in the result having an MSB of 1. This MSB is 1. So if this MSB is equal to 1, sign flag will be set. If it is 0, then the sign flag is reset. Again, this will be used for different purposes to identify what type of operation we are carrying out. If we are carrying signed arithmetic operation, accordingly we need to, it will be up to the user to interpret what is the resultant output. So this was about the ALU unit. ALU unit consists of the accumulator, the ALU itself, the temporary register, and the flag register. These are 8-bit registers, and they are used for carrying out the arithmetic and logical operation. It actually the processing takes place in the ALU itself. The second component that we had discussed is the general purpose registers. So we actually have, uh, as discussed, we have the arithmetic and logic unit, we have the general purpose register section, we have the timing and control unit, we have the interrupt control unit, and the serial IO control. We are done with the ALU unit. Now we are moving to the general purpose registers. So what is the general purpose register? It actually is the internal memory of the microprocessor. So two types of memory blocks will be, you will have the external memory that will be interfaced with the microprocessor, as well as you will have the internal memory of the microprocessor itself, where it can store data, process information, etc. So these registers, since they are internal to the microprocessor, these registers do not have any addresses. They do not have addresses, they have got names. Uh, some of them are 8-bit, some are 8-bit, some are 16-bit. So as we know, the memory can be, we can access 16-bit of memory using the 8085 microprocessor. So you have both 8-bit registers as well as 16-bit registers associated with the 8085 microprocessor. So what are the 8-bit ones? You have W, you have Z. These are they are named using alphabets. You have W, you have Z, you have B, you have C, you have D, you have E, you have H, and you have L. Apart from this, you have the accumulator itself that I told you is also a general purpose register. You have the temporary flag register, instruction register. All of them are also 8-bit registers. Uh, but separate from these known register types. They have specific purposes for which they are built: accumulator, temporary flag register. And 16-bit registers, you have the program counter. They will be used for specific purposes, these 16-bit registers. You have the program counter denoted by PC. You have the stack pointer, or stack register, SP, uh, and you have incrementer, oblique decrementer, address latch, ALR. You have the 8-bit registers, you have the 16-bit registers. Apart from this, the 8-bit registers can also be paired up to form 16-bit register pairs. They can be used in pairs. The combination with which they are actually used, it's fixed. You can combine W and Z. W and Z is combined, B and C, D and E, H and L. So these 8-bit registers can be used together for and as a 16-bit register pair. Among these, HL is one of the most important register pairs. Among the register pairs, it's one of the most important register pairs that's more frequently used, and it also serves as a memory pointer that we'll be discussing later on while we'll be discussing instructions regarding this. Fine, so a number of instructions will actually be based upon the HL register pair. Apart from this, the accumulator and the flag register, they can be paired and used as a 16-bit register pair, and they are actually used in stack instructions. So once we actually take up the instructions, we'll be studying a lot of instructions. We'll be understanding uh, each and everything that has been actually left so far. That will be we'll be getting that. So far. Right now, it is not possible to understand each and everything because we are dealing with a lot of things here. So the accumulator and the flag register can be paired up and can be used in stack instructions, and together they actually are known as the processor status word, ESW, ESW. Right? So this 16-bit register pair that will actually be generated, accumulator will form the most significant bits and the flag register will form the least significant bits. So these are different register pairs that registers. You have 8-bit registers, you have 16-bit registers, and you have 16-bit register pairs. This actually serves as the internal memory of the microprocessor to carry out various processing without accessing the memory outside, so they are much more faster to access as compared to the interface memory, and they do not need to be addressed. We do not have addresses to, for these registers. They have simple names, and they are accessed by the microprocessor directly. uh, so some of these registers are accessible, some of them are inaccessible. The accessible ones are, we can read as well as write onto these accessible registers. You have B, you have C, you have D, you have E, you have H, you have L, you have the program counter, you have the stack pointer, the accumulator, the flag register. These are the accessible ones. The inaccessible ones are W is inaccessible, Z is inaccessible, ALR is inaccessible, the temporary register is inaccessible, the instruction register is inaccessible. So these are about different registers of the microprocessor 8085. Now we'll be studying the 16-bit registers in detail, the program counter, the stack pointer, the ALR. Uh, so let's see how these registers are accessible using some examples. Say for example, we have an instruction move A, comma B. So using this instruction, what we can do is we can simply move the contents that are actually in the register B to the accumulator A. Fine. So this is actually shown in this fashion. Move A to B is shown in this fashion. Similarly, you can have instruction MVI C, comma 50. All the numbers, whenever we'll be writing instructions, these numbers are actually in hexadecimals, FT. So this instruction means simply move immediately the content that's actually the data that's actually given to us immediately to the register C. Fine. Or you can have an instruction like, these are different examples. You can have an instruction like add D. Fine. Now we understand that whenever an arithmetic and logical operation takes place, one of the operand is always in the accumulator, and second operand will be either in the memory or in temporary register. That will be placed through the temporary, or it can be in the register also. So here you have the contents are in a register, that's D. So it will be added with accumulator A, and the resultant will again be put in the accumulator only. Fine. So this symbolism that we are actually using here to show the operation, various instructions that are taking place. We are showing different kinds of operation. B is being stored in A, 50H is being stored in C, A plus D is being carried out, and that's being stored in A. This symbol that we have used to show these operations. This is known as the macro RTL of instructions. So it's one of the register transfer languages, the macro RTL, and we actually use in, we'll be actually also studying the micro RTLs of 8085. So this can be referred to as the macro RTL of 8085 or macro RTL of instructions. So this way we'll be actually, as we move ahead, we'll be actually using these types of symbolisms to actually identify what type of operation we are doing, what is actually being carried out, what is actually happening within the 8085 microprocessor using the macro RTLs as well as using the micro RTLs. So this is about the general purpose registers. So we have given a brief about the general purpose registers. We'll be studying in detail what happens with, what does program counter do, what does the stack pointer do, the stack memory, as well as the ALR. Right? So that's for this session.